more of a fun lecture today than anything else. I think at least I have found it to be interesting to learn about some of the medical history on the human side and the veterinary side. And some of those old pictures and some of that history is really fascinating. And radiology is the same way. How radiographs were discovered, how X-rays were discovered, and all of that. It's interesting, and I'm kind of a geek, but it's interesting to learn about that. And so that's what we're going to talk about today. And I think it gives you a good basis going forward. So that's what we're going to do. Again, there's my email. If you need to get a hold of me, that's how you do it. Okay, so when we're going to talk about radiology, if I can make it change slides, which is not wanting to do, there we go. Okay, so here we are. What are these things? This is a radiograph or an X-ray, if you will, of 4 different things. And so when you're looking at these, when we look at radiographs, it's a different way of looking at things. It's only black and white or shades of gray. So unfortunately, nobody's come out with color radiographs yet. Maybe down the road that'll happen, but I kind of doubt it. So I'm looking at 4 different things in one view of these separate objects. And does anybody have a clue what these things are? So if I'm looking, can y'all see my mouse pointer too or not? Perfect. Okay. So what is this thing? What the hell is that? Well, we don't know. What the hell is this? Okay. Anybody want to take a guess? Don't be shy. This is not a shy class. Okay. Nobody knows. What about this thing here? That's pretty tough. It looks like, I don't know, not much of anything. And then this thing looks very similar to that, but it's bigger. Okay. So can anybody tell me what these 4 things are? And I'll give you a clue. Everybody in here knows these 4 things. Okay. So one of the things I learned a long time ago that one of my mentors told me, if you don't know what something is radiographically, then you just describe the hell out of it. Okay. You may not know exactly what it is, but start describing it. And so if I look at all 4 of these things, number 1, there's 4 things. So that's a good start. Number 2 is, are they all well-defined or are the margins fuzzy? To me, they look like they're all pretty well-defined, okay? And they're all really bright white on this radiograph, okay? And we're going to talk about the different shades of gray that you see on radiographs, or the different opacities coming up. But all of these things are really pretty bright white. This one here has kind of shades of gray inside of it, so it may be a little bit different. So we don't know what the hell these are, and they're surrounded by this black stuff, okay? So all I can tell you is they're radiopaque, means they show up on X-rays. They're all well-defined, they're different shapes, and there's 4 of them. That's all I can tell you so far. So now let's look at another view of these things. So here's another view when I'm looking at. Okay, so here's the same 4 objects. So here's this one here, here's this one, here's this one here. Unfortunately, it kind of touches this one. But what are these 4 objects? Can you tell now? All I did is I moved it, and now we're looking at it from a different viewpoint. Okay, can I tell you exactly what these things are? Well, what about this one here? Anybody want to take a stab at that? What the hell is that? I don't know. It's still well defined. What is this thing right over here? What is that thing? You start to get a clue on that one, so somebody can speak up. I know you're not mutes because I heard you talking a while ago.
Light bulb?
It's a light bulb. Okay, very good. So we kind of elucidated that. Well, what about this thing here? Anybody have a clue what that is? It's tough. What about this thing here? It's still tough. And so here is another thing that you have to keep in mind. Anytime we're radiographing something, usually what we're radiographing is a 3-dimensional object, like an animal, okay? It has 3 dimensions that you can look at it. You can look at it from above it, from the side of it, and from in front of it. So there are 3 dimensions. Well, with radiographs, everything is summated on top of each other, and you're looking at a picture of it, a black and white picture, just in something in a piece of film or on your computer monitor that's sub-millimeters thick, right? And everything kind of stacks on top of each other and summates. And so sometimes in life, if you look at things from one direction or one dimension, you don't really get a good clue of really what you're looking at. It can cause problems and misconceptions about that object. So let's look at the third view. Since these are 3-dimensional objects, look at third view. Okay, so here's the third view. Now what are they? Aha, Now we all know what they are. Okay, so somebody take a stab at what is this thing here? It's
Staple remover.
Yeah, it's a staple remover, staple puller. And then we have this light bulb. What is this? If you don't know what this is, and you're just a dumbass. Okay, so what is this thing here?
Paperclip.
Paper clip, very good. And what is this? We don't see the end of it, got cut off, but what is this? Well, that's a pair of some bandage scissors. Okay, you don't see the blades, but they're over there. So that's some bandage. So here's the bottom line is there's 4 objects. Now we know what they are, but you know what happened is this view, if we would have started with that view, everybody would have known what they are. But in real life, typically, and unfortunately, none of us are lucky enough to always get the right view the first time around where we can recognize things. And keep in mind that all 4 of these things are things that you're familiar with in life. Okay, so that makes it even easier. Some of the pathology that we see on radiographs, whether it's in the lung or the spine or the limbs or the abdomen or whatnot, a lot of that stuff you're not going to be so familiar with the way it's supposed to appear. And so that makes it even more challenging. Okay. And not to count that we get films that have various quality, the animal may be moving, they're well defined, things like that. So anyway, that's what these 4 objects are. So bottom line with this is sometimes you have to get different views of even a commonly known object to be able to recognize what it is. Okay. If your luck is like my luck, you're never going to get this diagnostic view first time around. It will probably be the last one that you end up getting. Okay. So let's look at another radiograph. So here's another radiograph. Here, what the heck is this thing? Okay. I don't know. Okay. It's something. And again, we want to describe the hell out of it. So the margins of it are well defined. It's kind of an overall gray. It's not as white as those other things. So it's more of a soft tissue or less opaque structure. It's kind of tubular in shape. Okay. Do I see the edges of it over here? It looks like I do because here's where there's nothing. That's just air. And here's the object. And over here there is. But do I see the cranial end of it over here or the caudal end of it? No,
I know what it is.
Huh?
Banana. Is it a banana?
Could be, right? But we don't know. And why do I not know for sure what it is? Because I can't see all of it. Okay. If I do the other views, now I do see it and it's a banana, like you said. Okay. But it really helps to see the entire organ or the entire object. Okay. And I can't tell you how many times every day that we read radiographs of a dog that's vomiting and they only have part of the abdomen on the radiograph. Okay. It's hard to diagnose a dog that's vomiting if the stomach isn't even on the film. Okay. And so rule number 2 or 3 or 4 or 40 or whatever that we're going to look at here is not only do you have to get different views to recognize it, but you typically have to get the entire object on the same film to where you can see it. It makes sense and it's common sense, but it unfortunately oftentimes doesn't happen. Okay. Okay. What about this thing here? What is this? Okay. Again, if you don't know what they are, then describe the hell out of them. Okay. So are these things, if I was going to describe them, I would say, well, there's a bunch of them. Okay. I'm not going to count them, but there's a bunch of them. They are different sizes and shapes, but they're all well defined. They're all kind of round to oval in shape. The edges of them are well defined. The inside of them is kind of mottled in its appearance. And a lot of them have this radiolucent thing in the middle of it. Okay, that you can see. Some of them are well defined, but some of them, the lucencies are ill defined. That one's hard to see. Okay, so any ideas what are these? And again, these are something that you're familiar with. Okay, and it's also something that you probably wish you had some of right now. Okay, so what are these things? Somebody take a
Are they
step.
coffee beans?
Coffee beans would be a damn good bet, but it's not. Any other ideas? Okay, somebody, a lot of times people say grapes, and that'd be a good bet too, but they're not. So these are peanut M&Ms. Okay, and so the little loosen, if you ever break open a peanut in the middle of the peanut M&Ms, there's that little cavitary or that little hole inside the peanut when you break it in half, and that's what you're looking at here. So we don't know what they are by radiographs, by looking at them, because we've never seen a radiograph of peanut M&Ms, but now you have. Okay, so that's what these things are. So bottom line is radiology can be very challenging because we're looking at something maybe in 1 or 2 dimensions, even if they're commonly seen objects that we don't recognize because we're not used to looking at them in this modality of radiographs. Okay. Okay, so who invented X-rays? Well, it was a guy named, this guy here, his name was Wilhelm Conrad Röntgen, right? And he lived from 1845 to 1923. He's an interesting guy. He looks really serious there. He's obviously a very famous person for what he did. So we're going to talk a little bit about how he invented X-rays and how this came about, because it's a kind of a fun story. This radiograph that you see here is the first radiograph that was ever published of a human hand, and it happened to be his wife's hand. His wife's name was Bertha, and I'm not making that up. His wife's name was Bertha, and anyway, that she was the guinea pig, and then that's her hand, and she was the first one to get radiographed. So it made her hand pretty darn famous. Hang on, I gotta text my wife here real fast. Okay, done. Okay, so Röntgen. So what about him? Well, he's a German guy. He was born in Germany. And at age 3, his family picked up and left, and they moved to Holland. In high school and junior high, he was just an average student. He, didn't really try real hard. Maybe he didn't have to try real hard. I don't know. But he was B's and C's kind of a student, not somebody that you would think would be super brilliant, but he ended up being that way. And in high school, if you look at the history, and there's no real details on this, but he got kicked out of high school and expelled for some kind of joke or prank that he did, that all we know is it involved a girl. Okay. And so somehow he did something that probably wasn't, kosher at that time. And so they kicked his ass out of high school and expelled him for good out of high school. Okay. So he's not starting off very good, but he's feeling kind of sassy. He's winking here because, this prank that he got kicked out because of this girl. Right. Okay. So because of he never had a high school diploma, he never got out of high school. Back then, he was denied entrance to any college because there was no GEDs or equivalencies and things like that. And you had to have a high school diploma or you wouldn't even be considered to get into college. So every time he applied to college, he couldn't get in because he had no high school diploma, which would continue to haunt him going forward. So finally, somebody said, okay, we're going to make up this special entrance exam for our particular college. And if you can pass it, then we'll consider letting you into college. And finally, the second time around, he passed the exam and got accepted into a college in Zurich, Switzerland, and did well at that point in time. Graduated and got a mechanical engineering degree in 1865. And stayed on as a graduate student in academia. His interest was really on the various physical properties of noble gases. So that's what, he kind of specialized in, is looking at noble gases. And so now he's a little happier. He's got a smile on his face. He's in grad school, probably having a good time. He's got a mechanical engineering degree under his belt. So things are looking up for old Wilhelm Conrad Röntgen. Okay. Finally, after graduate school, he got his PhD in 1869, also in mechanical engineering. He met the love of his life after that, married Bertha Ludwig Röntgen in 1872. After that, he was offered a he got paid nothing at a new university that was desperate to have somebody, at the University of Würzburg back in Germany. Okay. And you know why they didn't pay him is because he didn't have a high school degree. Okay. It kept haunting him back then. Even though he had a PhD in mechanical engineering, he had no high school degree and he had to take something to start working. So finally he got frustrated there because he's working his ass off and not getting paid anything. So they're taking advantage of him. And finally he got accepted a paid position at a new university, the University of Strasbourg in Vienna. And so he went there and started working. Over time, in 1888, he became the head of the physics department back at the University of Würzburg, the same school that wouldn't pay him before, which I think is kind of ironic. So now Röntgen's happy. He's got a big shit-eating grin on his face, and this guy's got it made. He's doing really well, right? Okay. So during his career, he was awarded numerous prizes for his academic prowess and things like that. In fact, he got the first Nobel Prize for physics that was ever awarded in 1901. He was, by the English guys, he was knighted and granted the title Sir. But Röntgen, all throughout his life, was very humble, was not real high on himself, and he actually declined to accept the title. And for the rest of his life, even though he had that, he would not go by Sir Röntgen. So here he is now. He's a little more serious, you know, his eyebrows up in the air, you know, he's got some deep thoughts going on in there in his head. Okay, so here is a tombstone of him. Here lies Bill. Bertha gave him a thrill. Sure wish I was in his will. Okay, now how many think that's his real tombstone? Okay, probably not. It's not, but somebody made it up, but it's kind of funny anyway. He died in February 1923, and at his request, all of his documents, correspondence, letters, notes, academic stuff was cremated along with him. So he has no grave anywhere. Okay, which is kind of unfortunate. It was kind of be fun to look at some of those old documents. So how did he come across? Here's this interesting dude married to Bertha that's interested in mechanical engineer, interested in noble gases. So how did this guy discover X-rays, and how did that happen? Well, it happened like a lot of discoveries, happened totally by accident. And on Friday, November 8th in 1895 is when it happened. He discovered X-rays and didn't know what the hell they were, which I'm going to tell you how that happened. And he named them X-rays after the algebraic unknown X. You know, when we did algebra, we'd always solve for X because we didn't know what X was going to be. So he didn't know what these things were that he discovered, and so he called them X-rays, right? It was first reported in the literature of his discovery in 1895. There's a paper called On a New Kind of Ray, a Preliminary Communication. So that was the first published paper on what these X-ray things are. So here's a picture in his lab. And now from what I understand, I've never been to it, but in Germany, there is a museum in the building where he used to teach, and his lab is still set up where, you know, Röntgen did all of his work, him and Bertha. Okay, so in here, you know, there's this table in this lab, and this was an electric coil, you know, and back then that there was no electricity really, and so they would rotate this thing around, and it would generate an electric charge and generate electricity, and that then it was fed with a wire, the electricity, to this little teardrop thing here, which basically was a big light bulb, a big thick light bulb. And back then, people played with these things, and it was called a Crookes tube. Okay, so it was great, a great big light bulb that would kind of glow when you would spin this thing around and would supply energy to it. Okay, and so people played with them. They didn't really know, you know, what it was, but it was kind of cool. And then so he had a stool here. That's probably his briefcase with all this stuff, some tables, and who knows what all this stuff is around here. There's a fan in the room. You see that? So he's got this fan in the room because it was probably hot. Didn't have AC back then, and so that probably kept him a little bit cool. And some over here on this table over here, he had some pieces of paper that he would use to write on. And back then they didn't have paper like we have right now. You know, it's not made out of wood pulp. It was made, this paper that was made out of this special stuff, made out of this stuff called barium platinocyanide paper. Okay, and so it was kind of this weird paper, but that's what everybody used back then to write on and things like that. Okay, so that was kind of the setup with his lab. So how did he discover X-rays? Well, he would turn that Crookes tube around like that, you know, and it would make energy. And working along with Bertha, then he would turn the Crookes tube, and they noted that the paper, that barium platinocyanide paper, seemed to glow a little bit. It got brighter, and the faster he would turn the Crookes tube, the more the paper would glow. Okay, and so he thought, well, that was pretty cool. But he thought, well, you know, maybe we're just imagining this. And so he said, maybe we can see it better if we do it at nighttime, or, you know, get the lights on the room down or something like that. So he did, and you know, cranked up that Crookes tube, and sure enough, they proved that this paper was glowing, and they didn't know why. Okay. But he decided that it had to do something with spinning this electric device and this Crookes tube. Okay. And so he decided, well, you know, what we're going to do, being the good scientist, the kind of thinking kind of person that we are going to do a little experiment. So we're going to do this black box experiment that was reported. And so he decided, well, we're going to block out all visible light. So he put this black cardboard box around the Crookes tube. And of course, when this generated light that we could see, it would get stopped by the cardboard. Okay. So he decided, well, that's what we're going to do. We'll put this big box around it. We'll repeat the experiment and see what happens. And guess what happens? He spun this thing around. He said, Bertha, go over there and tell me if those papers still glow or not with this black box on the Crookes tube. And guess what happened? The papers still glowed. Okay. So now he knew that he's onto something. It's not visible light, but it's something else that's coming from this Crookes tube that's causing these papers to glow, you know, when he activated it. Okay. And that's what he determined. He didn't know what it was. So let's just name it X. So X-ray. Okay. So he ended up doing a few other things going forward to try to narrow it down a little bit. So he, around the Crookes tube, he would put a thicker sheet of paper or cardboard around it to see if that would stop the glowing. And of course it didn't. He put a thicker book between there and where the paper was, and that didn't stop it either. He put some wood in between there, and that didn't stop it either. And so finally he said, well, I'm going to put a little sheet of aluminum or metal between there. That didn't stop it much. It still glowed, but maybe a little less intense. And finally he got around to sticking a piece of lead between the Crookes tube and the paper, and that stopped it completely. Okay. So now he's learned, here's some things that this, whatever this X-ray stuff is, it penetrates through cardboard and thick books and wood. It penetrates mostly through aluminum, but it can't penetrate through lead. Okay, so he's narrowing this down as like the good scientist that he has. And then he would go over there and he would put his hand near the paper, and Bertha would, and he'd say, oh, holy shit, man, I can see the bones inside your hand. And so finally he said, yo, woman, stick your hand up there on that paper and keep it there for a while. And she did. And guess what happened? There's the first X-ray. Okay. So now he's really onto something. Okay. So there's, you can see there's her wedding rings over here on Bertha's hand. And that's the first X-ray ever produced. Kind of cool. Okay. So then he's still, again, the scientist inside of his head, he's thinking, okay, I got to prove this before I write this up. Let's do a few more little thoughts and experiments here. So being skeptical, he decided, well, maybe it's something on this paper. Maybe it's you know, this one sheet of paper that's doing it. So he kept extra paper of the same type in a drawer, and he opened it up, and he noticed that on the paper that has been in the drawer, that it had its X-ray already made from all the exposures that he'd been making in the lab. And so on that paper, he kept a set of brass weights on that paper. And this is an X-ray of the different sizes of brass weights on that piece of paper inside the drawer. And he opened up another drawer, and there was all this debris of metal coins that were broken apart and stuff like that. And he had an X-ray of these metal coins also. And so he thought, well, that's kind of cool. So it's not, now I know it's not just the one sheet of paper, but all of this kind of paper, we're getting these images that are on. Okay. So what ended up happening, of course, back then, they didn't know what X-rays were. That's why they named them X. They had no idea that this stuff might be harmful to you. I mean, that was not even in their minds at that. They were trying to discover stuff about it. You know, and if you go back to his lab here, you know, here's the X-ray producing device, this Crookes tube. There's no lead shielding around, there's nothing. And so every time they would turn this on, it would stay on for however long you wanted to rotate this energy thing around. So it could be on for minutes. And it's constant X-ray exposure, not like we have now where it's on for, you know, 0.002 of a second. Okay. So it's constant X-ray exposure, pretty high energy stuff. And so they didn't know that this stuff was going to be harmful down the road. And basically back then, they really didn't see a whole lot of medical use for it. But the big use and how people were making money was they would sell these X-ray producing devices, and you could actually buy them from like the Sears Roebuck's catalog, and Amazon. No, not Amazon back then, but you could buy them from catalogs and order them. Anybody could. They were pretty expensive in the day, and so people would order them, and they would get them, brought to their house, and they would hold what's called ray parties. And so this was about the same time in medicine that they were also discovering anesthesia. And so, that was when they used to use ether. And so the affluent people of the day, they would have parties, and they would invite people over, and they would sniff a bunch of ether, and then they would have X-ray parties. And so they would get high on the ether, and they'd start shooting X-rays of themselves. And that was that was entertainment back in the day. So the real use for this was a novelty, not so much for medicine. And so here's some signs that, this was in a carnival, that you could go in this tent and get an X-ray picture of yourself, and take it home, so people would go get like family portraits of X-ray pictures of them and their kids and go take them home and hang it on the wall. Okay. And so here, before leaving the exhibition, see the wonders of X-rays, the greatest scientific discovery. You can see through a sheet of metal, through a block of wood, and even count the coins in your purse. Admission was $3 back then. That was a lot of money back then. Open all day. X-ray photographs were taken. And so you could go get these X-ray photographs and be a proud person, take it home, hang it on your wall of you and your kids in black and white, right? So here's it. And then they would open up in strip centers. Next to Walmart back then, you would have these X-ray studios that would open up. Okay. And so here's this guy that's in the strip center. He's got his little tube here, electronic device that we'd spin around. Here's the Crookes tube, and here's a lady with her hand down here. And of course, they're radiating the piss out of everybody around here because there's no shielding. And she would get bone portraits and take them home, and again, give them for Father's Day, this lady would take them home, and she'd say, "Here, honey, I got this picture of my hand, and I hope you like it." Okay, and that's what they would do back then. It's kind of crazy when you think about it. And again, here's one is in the Sears catalog. So this was an X-ray producing device that you could order from Sears back then and get it delivered to your house, and then you're all set up. Now you just got to order some ether, and you're ready to go have a big party. Okay. So finally, it started going on. They started saying, "Hey, I can see the bones in my hand, and so maybe it has a medical use." And so this is an early radiologist or scientist that's looking through this thing called a handheld fluoroscope. And basically it had like fuzzy stuff around here, would shield the light away from the eyes. So you'd peer into this thing, and it was all black in there. And it had a piece of that barium platinum paper on the end of it right here. And if you had the Crookes tube way over here somewhere, then you stuck your hand or whatever object in the middle, then you could see your hand. You could wiggle your fingers like that and actually see it in real time, like we have now with fluoroscopy. The image quality was piss poor, but it was still kind of cool, right? The problem is, again, there was no shielding. All the X-rays were going everywhere in the room, and also straight into this guy's face. And the more he did it, the more exposure that obviously he had at that time. So this is a typical radiologist or physician's office at the time. And this is still kind of funny when you think about it now, especially with all the HIPAA rules that we have in the United States, about patient privacy and all of that. But you could go into back then you could go into it if you knew it was a really good surgeon. If you walked in and his lab coat had blood and pus and everything else all over it, because that showed that he was experienced, that he's done a lot of procedures. Okay. On the other hand, you could tell if it was a good experienced radiologist because he would hang these X-ray portraits all over his office of all this work that he's done before. And that would impress people when they came in and thought, well, this guy's pretty good. Okay. And so you can see all these X-rays of these people, X-ray pictures of people hanging in his office. And so here he is. He's bent over looking at this guy's chest through one of these handheld fluoroscopes. Here's the Crookes tube right in front of it. So he would look in and you could probably see a little bit of his heart and his lungs, like on one of these photographs of this guy's chest, right? So, and then they finally morphed into other things. And I actually remember this when I was growing up. We would go, to the mall, of which there's hardly any malls around anymore. So that's kind of changed too. But we'd go to the mall, we'd go to a shoe store to get new shoes. And I remember going in there, and they would have these things here. I think there's a picture right here. And this was you would commonly see these machines in shoe stores, and they had three little lookout things that you could look in here. One's for the person getting the shoes, because you'd stick their foot in this chamber, and you'd put these new shoes on that you were fixing to get, and you'd look in here and you could wiggle your toes and actually see your toes moving in the shoe and see if it was rubbing on part of the shoe or not. Okay, so you used it to see if the shoe fit, literally. And then you'd have two other ports over here that the salesman or his manager could look at, and they say, yeah, it fits perfect. You should buy these shoes, right? And so these shoe store fluoroscope, that's hard to say, were very common. And of course, this was an X-ray tube, and it's shooting directly up from the bottom through her feet, into her uterus, into her ovaries, into her head. And everybody's looking at this. And it was common to find these things in malls at the time. And this was back probably in the mid 60s, early 70s that this was happening. So not even that long ago. So it's crazy when you think about it. So there's an X-ray of somebody's new shoes that they're getting to see if their foot fit in the shoe, right? So obviously none of this was good, and they ended up finding out that over time that radiation safety is important. That radiation exposure, the more you get, is not a good thing. And so we had to talk about, we have to talk about radiation safety, and that is important. And so that's where we're going to go next in this little lecture. Okay, so now that we know how X-rays were discovered and things like that, and we know who Bertha is, so everybody knows who Bertha is now, so that's a good thing. So we have to go forward and talk about X-rays and really what are they, now that we've learned a little bit more about them. Well, X-rays are a form of electromagnetic radiation. It has a waveform physically, so it's very similar to visible light that we see. And we all learned from physics that electromagnetic radiation, there's a spectrum. So visible light is only a very small part of that spectrum. And on one side of that spectrum, we have infrared light and ultraviolet light. We have radio waves, AM and FM radio waves. We have microwaves that's in that electromagnetic spectrum. And then far on one side of that spectrum, we also have X-rays and gamma rays. But it's all this wave form of energy, okay? There's two types of radiation that we see. One is called non-ionizing radiation, and the other is called ionizing radiation. Well, non-ionizing radiation, for the most part, at least that we know of now, does not harm you. And that's like microwave energy, like in your microwave oven. It will harm you if you stick your hand in there, but otherwise, no. And the other type of non-ionizing radiation that's commonly is visible light that we see, okay? So non-ionizing radiation is not a big deal. Ionizing radiation, on the other hand, is, and that's the dangerous part. So we have X-rays and gamma rays are the two harmful types of ionizing radiation. And why is it harmful? Well, those type of ionizing radiation of the electromagnetic spectrum, they have the ability to impart energy into orbiting electrons of your body, and even interact with the DNA inside your cells inside of your body. And they can rearrange things, because when they impart that energy, that can cause problems. And the problems that it can cause is potentially it will cause cancer sooner rather than later, or it can cause genetic defects that may happen not to you and not to your kids, but 2 or 3 generations down the road. You may have a kid with like 8 fingers or something like that, and it's all because granddad had too much X-ray exposure. Okay, so there's 2 types of ionizing, or there's 2 types of damage that can occur due to ionizing radiation. And so let's talk about these. One of them is very common. One of them is not as common. Okay, so the direct cellular damage is where you have an incoming X-ray, or photon is really the name of it, that comes inside your body, and it interacts with a cell inside your body, and it directly, that's where it gets its name, direct cellular damage, directly damages a piece of the DNA inside that cell. So that's direct cellular damage. X-ray coming in and directly damages the DNA. Okay. The other type of damage that can have from ionizing radiation is indirect cellular damage. So how does that differ? Well, indirect cellular damage, kind of like the name would imply, you have an X-ray photon that's coming in and it doesn't interact with the DNA, it interacts with the water molecule that's inside the cell. And it changes due to imparting energy, it changes that water molecule into a highly reactive, what's called a free radical or a peroxide. So it alters the water molecule. And that peroxide or the free radical then in turn damages the DNA. So it's an indirect damage to the DNA due to these free radical high energy things. Okay. The indirect cellular damage by far is the most common way that cells are damaged from ionizing radiation. Okay. So the indirect is much more common than the direct damage. Does that make sense? Yep. No. Okay, so there's also things we need to keep in mind that will alter how much damage could be imparted into a cell or being by the radiation. And these are pretty much intuitive if you have a little bit of common sense and think about them. So one is the dose rate. Okay, do you think it would be, if you're thinking about this, would it be better or less damaging to have a bunch of radiation delivered really quickly or spread it out over 40 years? The answer is it's going to be much more damaging if you get it all at once. Okay. If you spread it out over years, maybe the body has time to fix the little bit of damage that happens every day on its own. Okay. So the dose rate, the slower the dose rate, the better it is for you. If you get the dose, X amount of X-ray energy and you get it all at once, that's not a good thing. Okay. Also, things that will impart or affect how much radiation damage there may be is the anatomic part of your body that is exposed. For the most part, cells in your body that constantly are undergoing turnover, okay, will be much more sensitive to radiation and be damaged a lot easier than cells that never have much turnover. So what do we have what type of cells in your body have a lot of high cellular turnover? Well, the cells that line your GI tract, the crypt cells in your GI tract are constantly sloughing off and constantly making new ones. And so X-rays will damage those type cells much faster than it will, say, a cell that's in an osteocyte that's in a piece of cortical bone. Okay. Another type of cells, what's another type of cells that's constantly, your body's constantly making new ones and getting rid of old ones? White blood cells and even red blood cells. So X-ray is very damaging to white blood cells particularly. Okay, so any cell that has high turnover rates is going to be more susceptible for X-ray damage. Okay, and then the total dose delivered, that will also play a role. And obviously, again, it's intuitive. The more X-ray dose you give somebody, the worse it is. Okay, so that brings us to slide number 41, which we're going to talk about right after our 10-minute break, because I have to pee. Okay, so let's take a 10-minute break, and then we're going to come back. How is everybody? How is the fun meter? How is your individual fun meter? Okay, not bad. Okay, we'll keep that going, and I'll see you in about 10 minutes. Okay, is everybody ready? Everybody bladder's empty now, feeling a little better? Perfect. Okay, I do. I know I feel a little bit better, so that's a good thing. Okay, so let's continue. So we left off with this slide here, talking about the effects of radiation exposure and radiation safety. These are the acute effects. So just as that would imply, these are things that can happen to you relatively quickly after radiation exposure. Now, these things that we're going to talk about here, these 4 things coming up, these acute effects of radiation exposure, these are after a whole boatload of radiation all at the same time. So there's levels in here called, like 900 to 10,000 rads. That is a boatload of radiation. So this is like you would get not from working in a hospital. This is like you would get from walking into a nuclear reactor that's melting down, kind of thing. So that's the kind of level. So nothing like medical use of radiation, which we're going to talk a little bit more coming up. So the first one is the mildest of all of these. It's called, let's see, actually, you know what? Now my computer's frozen up again here. Hang on. Let me try to change why it's doing this. There we go. The most mild one is this one here after less than 300 rads, which again is a very small amount or a very large amount of radiation. So the first one is called the prodromal syndrome. And this is the mildest one of these acute effects that's described in the literature. And the prodromal syndrome, the person's going to experience some mild things like dehydration. Literally, they'll get a sunburn if they were exposed to that level of radiation. Because of the dehydration and the sunburn, just like anybody that goes and sits in the sun, you probably get some headaches. Your head kind of hurts a little bit. You don't feel as chipper as normal, so a little lethargy. Doesn't cause any death, and this will last from a few hours to a day or two, and then finally you get a little bit better. The next syndrome is called the hematopoietic syndrome, and this is after you get 300 to 600 rads, which is more radiation. And this one, again, this is the thing that's going to start to affect these type of cells in the body that have high turnover rates. And so we're going to have decreased white blood cell counts. You're going to have platelets that platelet count will go down. And because of that, you'll start getting hemorrhages and infections. The person's going to be more likely to get an infection because their white cell count's down. And if not treated accordingly, then these people can die within 10 to 60 days, and usually due to some type of septicemia or infection. The next level of exposure goes up to what's called the GI syndrome, and this is where you can get 900 to 10,000 rads, so just a whole boatload of radiation. And again, this affects the GI crypt cells that have high turnover rate along your small intestine and your colon, and that results in massive dehydration, vomiting, diarrhea, and again, septic conditions. And this one, you're going to have death that, unless severely treated in the right way, you're going to have death in this particular case that can happen in 3 to 5 days, usually due to complications with infection and dehydration. And the last one is when you get, it's like you were sitting on top of a nuclear reactor when it decided to quench. And so this one is you're going to get the CNS syndrome, and this is after 10,000 or more rads, and you will get massive cerebral edema and brain damage, and death occurs usually within minutes. So that's not a good thing. So those are the acute effects of radiation that's described in the literature. The late effects of radiation are things, obviously, that's not going to show up right now, but it may show up down the road for you. The somatic effects are things that can happen to you. If you were exposed to a lot of radiation when you were 12, let's say, and this may start to show up when you're turned 60 or 70. So premature aging, cataract formation, and neoplasia, squamous cell carcinomas, especially in your digits or your hands, leukemia, bone cancers, things like that. The great majority of all of those radiation workers back in the early days, including the Röntgens, including Madame Curie, a lot of those early radiation workers, they all died of leukemia. And it was probably due to their exposure because they didn't know any difference. The other types of late effects are genetic effects, and these aren't going to affect you necessarily, but again, this may affect generations down the road that's in your history. Okay, another thing we should briefly mention is this threshold versus linear concept of exposure. There's different thoughts on how radiation and how much radiation can actually cause damage. For the most part, most people nowadays go with this linear model, and that means even a little bit of radiation here will have a chance of causing a little bit of tissue damage, and it's little. So if you have a little radiation, you may get a small amount of tissue damage. If you have a lot of radiation, then you may get a large amount of tissue damage. And so most people will go with this linear model, and I think that's probably the best one, the most logical one to kind of go with. The other model is the conservative approach. And this says that with the conservative approach that you can get a fair amount of radiation, even a little bit of radiation, and it will definitely cause tissue damage. Okay, so that's a little more conservative. The other model is called the threshold model. And this is where you can get a fair amount of radiation, but up to a point, it doesn't cause any damage at all. Okay, so that once it reaches that threshold, then you can have the chances of getting tissue damage. And there's also another approach, this approach called hormesis, which makes a lot of sense. And there is papers written about this hormesis theory. And hormesis means that radiation is kind of funny because we just said radiation is bad for you and it can cause cancer. Well, what else can radiation do? What do they tend to treat cancer with? Radiation. Okay, so it can cause cancer, but it can also cure cancer, which is kind of weird when you think about it. And the reason being is, again, we take advantage of this fact that radiation tends to harm more tissues that have high turnover rates. And what is neoplasia? I mean, literally, what is neoplasia? It's uncontrolled growth of a particular cell line or organ, okay, with high, fast turnover. And that's why most cancers are very sensitive to radiation. Some aren't, but most of them are, because most cancers have high cell turnover rates. Okay, and so there is this hormesis theory that says that if you get over time, like every day you get a little bit of radiation, then maybe that's actually good for you. Because if you start to get, let's say you get one or two cells that decide they're going to become cancer cells and have uncontrolled growth, this little bit of radiation that you may get every day will kind of nip that in the bud and be able to go ahead and kill those cells that start to multiply if you didn't have the radiation. Okay, so the hormesis theory actually thinks that a little bit of radiation every day for you as you grow up is actually a good thing, because it may help prevent some cancers that start to form, which intuitively it kind of makes sense. Now, most people aren't going to live that. Most people are going to, again, realize that, this conservative linear approach is probably the best one to take, that a little bit of radiation still isn't good for you, that it has a potential to cause some tissue damage. Okay, in the US, we have, and I'm sure Canada is pretty much the same way, is that we have what's called the MPD, or the maximal permissible dose that a person can have. And it's based on a yearly dose rate. And now we're in another unit of radiation. Remember, we were talking about the prodromal syndrome and all of that. That was greater than 300 rad a rem when you would get that. In a typical radiation worker, we're getting much less radiation exposure. So depending on the tissue that you have, whether it's have high turnover rates or not, it's more conservative. So considered safe, if you get 5 rem or less in a year to one of these organs, that's still considered very safe, and you really have nothing to worry about. Okay. If you can get it, there's other tissues like your skin and your hands and things like that are more radiation resistant, and you can radiate them more and you still don't have anything to worry about. And even other things like your feet and your head, things like that you don't really have to worry about too much. They can even get more radiation and really not cause a big problem. So there's levels that the radiation medical physics people have researched, that if you're under these levels as a radiation worker in medicine, that you probably will be fine. You don't have anything to worry about. But of course, we always want to minimize it no matter what. Okay. Then you can use that and you can calculate how much radiation exposure one person can get depending on your age. Now, how many of you worked for vets before? Okay. I know most of you probably have. Hopefully all of you have. Okay. And of those that work for vets, did you help them shoot x-rays? Okay, so you probably did. And when you helped them shoot x-rays, were you ever holding the animal in the room while they're shooting the x-rays? Probably did, because most people, other than New York, which is illegal to do that, that's what most happens in most places, right? Well, guess what? Every time you hold an animal, you are getting exposed to some radiation. It's very small amounts, but the fact is you're getting exposed to radiation, and therefore you are considered a radiation worker, okay? Because part of your job is you work around radiation, okay? So let's say that Katie works at ABC Animal Hospital for 5 years and she gets pissed off, or they get pissed off, or something happens and it goes south. And now you're going to move from ABC Animal Hospital. Now you're going to go work for DEF Animal Hospital. Okay. Well, when you quit, you wore that radiation badge that whole time, which we're going to talk about. And that measures how much radiation exposure you had over time at ABC Animal Hospital. Well, when you quit, you're supposed to go to ABC Animal Hospital and say, I need a copy of all of the radiation stuff for me during that time. And then you take that to your next employer. And over time, you keep track of that yourself. And that way you can calculate over time how much total radiation you've ever had in your life from being a radiation worker, right? Unfortunately, most people don't do that, but that's what you're supposed to do. Okay. So if you know that over time, you can actually calculate how much is your maximum accumulated dose over time. Okay. And this is, would never ask you to do this, but on a test, but this is how you can calculate it, where N is your age. And so let's say that you're 25 years old. So that means N equals 25. So 25, and you subtract 18 from it. Well, why 18? Okay. And that's because that's when you're not a minor anymore. You're an adult. Okay. And in every 50 states in the US, it is totally illegal for anybody under 18 to be in the room with radiation. So you can have the high school kid that is 17 holding an animal while somebody's getting x-rays. Okay. That's illegal in every 50 state. Unfortunately, it happens. It happened to me. I worked for vets when I was starting at 13, and even then, back then I was in there holding animals, okay, which isn't quite legal, but that's why that number 18 is in there, because you're not supposed to, no matter what, anybody under under 18, you're not supposed to be shooting x-rays. Okay, so you take 25 years of how old you are minus 18, and you multiply that times 5, and the 5 comes from this number right here. Okay, that's the most conservative approach of what's safe. Okay, so if you do that when you're 25 years old, if you've had 35 rem of accumulated radiation total in your lifetime, you're fine. You don't have to worry about anything. And in reality, most hospital workers, even if you were like a human RT and all you did for a living is shoot x-rays, it's going to be way, way, way below this. Okay, not even close to that. Okay. Okay, so how do you minimize your exposure to radiation? Well, there's different ways to do it. One is time. So it's probably best if you have something that's emitting radiation near you, it's probably best to minimize your time around it. That's kind of intuitive, it makes sense. So one is time, minimize the time of exposure, okay? The other one is the distance. So the further are you away from the radiation X-ray tube, the better it is. And in fact, that's a huge player in this, that the amount of dose is actually, you can calculate it. It uses the inverse square law. So if you double the distance away from the X-ray tube, it actually quadruples the amount of reduction of dose to you. So the more distance you have, the better. So don't stand right next to the X-ray tube. Try to get away from it as best you can. Okay. The next one is shielding. And that's why we wear our lead gloves and our lead aprons. So we wear this thin sheet of lead, and it helps to shield you from the radiation, because just as Rinkin showed us, the x-rays have a real hard time penetrating through something that is lead, made out of lead. And the next thing that we have to do is this personal dosimetry. And that's where you wear the little ring badge, or you wear a badge up at your collar. And that measures how much radiation you've had in a period of time. Okay. So early on, once they discovered that X-rays were bad, this is what people would wear. It looks kind of funky now, but at least they discovered that X-rays are harmful. And so people started suiting up with lead gowns and hats and masks and everything else. Okay, so nowadays we have this lead apron. So this is an employee, she's shooting X-rays and has her lead apron on. And then up here near the neck area is the film badge, okay? Well, the lead apron is shielding, so that helps protect her from the radiation that's being in the room when you're holding an animal, okay? The film badge does nothing to protect you. It's not like a cloak. It's not a shield. All it does is measure the amount of radiation that she was exposed to. And depending on what clinic and how much you use your X-ray machine and the laws in your state, you have to replace these film badges a lot of times monthly and sometimes quarterly. And inside that film badge is a little piece of X-ray film, and you send it off to a processing lab, and they measure the amount of exposure and then measure that, put a number to it, and send it back on a piece of paper to the employee. And that's how you keep track of how much maximum exposure that you had with the film badge. With the film badge, you're supposed to wear it outside of the lead apron, okay? Because again, you're trying to measure the amount of maximum exposure. It wouldn't make sense to wear it inside the lead apron. So outside the lead apron, and you're supposed to wear it at a collar level or down at the belt level is where you're supposed to wear it, okay? Now we know, and we're going to talk a little bit about this when we start talking about how an X-ray is produced here in a minute. And this took me a long time when I was in your stage to kind of grasp this concept. Okay, so if I look here, here's the dog's rib, here's the X-ray of the dog. Okay, so I can see there's some ribs here. It's the left side of the dog sitting over here. Okay, this black part of the film is where you would collimate in, and it's a beam restricted device, so you can vary the size of what's being irradiated, right? And we all did that. If you shot X-rays, you kind of twiddle the knobs of the X-ray tube, and you could vary the size of the primary beam. Okay, so this is the primary beam. That's the part that's going to give us a medical image. Okay, but in reality, if you go outside of the primary beam over here, you still have very low level X-rays, but they're also not that low level because you can still see the bones in this person's hand. Okay, so where does this X-ray energy outside of the primary beam come from? Well, that's called scatter radiation. And it's not leaking from the X-ray tube. The scatter radiation actually comes from the animal. What ends up happening is the primary X-rays go into the animal and they interact with all the cells in the body. So liver cells, lung cells, bone cells, any cell that interacts with. And inside the animal, it generates more X-rays. And they're very low level X-rays, but they go out in every direction. Okay, so all of this X-ray outside of the primary beam is called scatter radiation, and it comes from the animal, not the X-ray tube. Okay, but it's still energetic enough to where it's causing enough exposure to your fingers where you can actually see your bones inside your finger. This is what causes your exposure to go up. Okay, and even if you wear lead gloves, if you have all the lead gloves that you wear on your fingers, they're only designed to protect you from scatter low-level radiation. If you have a lead glove on and you stick your fingers in your hand inside the primary beam, you're still going to get a lot of dose. Okay, they're not designed to protect you from primary beam radiation, only from scatter radiation. Okay. Nowadays, there is absolutely no excuse for something like this. Okay, this is horrible. This is if you work for a vet that does this, all that tells me is that they do a poor job of probably anything they do as far as animal care, surgery, and anything else. And the vet's ignorant and stupid, and you need to find another job. Okay, because there's just no excuse for this kind of stuff at all nowadays. Okay, so here we have, here's a cat. Here's a skull and spine, and here's whoever's holding this cat with, and they're getting their shit radiated out of their hands. by this x-ray, and you do this time and time and time and time again, and your dose starts to add up, because now it's not even scatter radiation. Now you're in the primary beam. Okay. So there is absolutely no excuse for that kind of stuff nowadays. If you see that in a clinic you interview, walk out the door, go somewhere else, because that means they do a crappy job and they don't care. Okay. If you do that long enough, this is what happens. This picture and the next one is from these early radiation workers that got a shitload of radiation, right? Not anybody nowadays that would get a modest amount of radiation. But this is squamous cell carcinoma that's starting to form. It's got a few digits that have already been amputated because of it. But this is squamous cell that's starting to form on the digits from this radiation worker that probably had his hands inside a fluoroscope for a long time over time. And remember those guys that I showed you the picture, they're staring back in the old days directly into the x-ray tube with that, you know, that handheld fluoroscope thing. Well, that thing right there, this is what ended up happening to a lot of those guys. So here, that's where his face was starting to slough off. That's from a lateral view of it from that guy. So you don't want to be that guy. I can tell you that, right? And again, that would never happen nowadays, but back then it did, because they didn't know what they were doing. Okay. So again, back to the film badges now. The film badge monitor, you need to know, again, what is it? How do they work? And there's other types of monitors called a TLD monitor. I could care less if you know how they work. The bottom line is, what you need to know is they measure the amount of radiation exposure you had for a period of time prior to when you sent it in to be measured. Does that make sense? That's basically all you need to know. Okay, and then when you get that report back, they send it back to your employer, and the report will give you in units of how much exposure that, you know, Shannon had. Okay, and it will come back usually in rad or rem, but there's different measurements of radiation. There's Röntgens, there's rad, there's rem. For your practical purposes as a veterinarian, they're all the same. So it doesn't matter what you call them, and one equals the other. So one rad equals a Röntgen equals a rem. So that's all you need to know. So it doesn't matter what unit it is, they're all about the same. Okay. Now, if you look at the big picture of radiation in the world, okay, there are man-made sources of radiation, and these are like medical images and x-rays and gamma rays and stuff like that. And there is natural radiation. So natural radiation is radiation that we can't do anything about. We can't minimize it for the most part. And it's radiation that's just in the earth, okay, and coming from space and cosmic rays and things like that. If you add up to 100% man-made versus natural radiation, only about 18% of the average person's radiation exposure comes from man-made radiation. So the great majority of it, 82%, comes from stuff we can't do much about. Okay, and that would be internal radionuclides like potassium-40. Where would you find potassium-40? Anything that has potassium in it. So bananas. Okay, a certain amount of that potassium inside bananas, and if you have no salt, like KCl salt and stuff like that, some of that potassium is radioactive, and there's nothing you can do about it. Okay, terrestrial, that's radon. So in different parts of the country, there are radon levels that live in the earth are higher than other parts of the countries. Okay, cosmic rays. This is rays that come in from the outer space. You know, our atmosphere is supposed to shield out most of that, and it does, but we still get some that penetrate through the atmosphere. And so all of that natural radiation contributes to 82% of a person's radiation exposure. So only 18% is from man-made stuff that we're talking about. So then you kind of ask yourself, well, why would I even work with radiation? Okay, well, it's because no matter what you do in life, there's a risk. Okay, if you want to go live in Grand Cayman, what's the risk? The risk is you're going to have a hurricane that's going to come kill you. Okay, is it a big risk or a pretty small risk that you're going to die from a hurricane while you live in Cayman? It's pretty small, really. You might get hurt. You might have to move away for a little bit, might damage your house, but the overall risk is pretty small. So why would you accept that risk? Well, you accept that risk because number one, maybe you're going to vet school and you're going to learn how to be a veterinarian. So the benefit outweighs the risk. Okay. Everything you do in life, there is risk benefit. Okay. If you drive your car, down to the grocery store, there's a risk. The risk is you're going to get in a wreck and it may not even be your fault on the way and you might get killed. Okay. But the benefit is you have to go buy groceries and because you have to eat, feed your family. Okay. So again, everything there is a risk reward, no matter what you do. Okay. Some things you do that the risk is higher. If you're a race car driver, then your risk from driving around in a race car is going to be much higher than if you're going to the grocery store. Okay. But you accept that risk if you're a race car driver. Why? Why would you accept that risk? Well, because you think it's fun. Okay. So you get enjoyment out of it. Plus, you probably get paid a lot of money. Okay. So there's risk reward there. And it's all personal. And you think, well, for me, the reward is greater than the risk, and whatever activity you want to do. Okay. Radiation worker is the same way. Okay. So as a veterinarian, if you have an x-ray machine, you again are classified as a radiation worker. And you do that. Why? Because you are a veterinarian and you want to help animals and you want to treat animals. And bottom line is you have to make a living. Okay. So you're going to make money as a veterinarian and take care of you and your family. Okay. And you accept that risk of working with radiation because the reward for you is greater than the risk. Okay. So this is an interesting chart that I found years ago in a book of medical physics. And if you look here, it's kind of interesting because if you look, this is the number of days taken off an average person's life for these reasons. So these are the risks, okay, that you would accept. So the number one thing on this list that will take 3,500 days off your life in total is if you're an unmarried male. Okay. And why is that? That's because unmarried males are stupid for the most part. Okay. They're taking undue risks. Why are they taking undue risks? Because they're out bird dogging trying to find a girl. Okay. So they're out at the bars, they're out doing things they probably aren't real smart to be doing. And all in trying to do that is to find a mate. Okay. It's evolution. It's kind of the same thing with tigers and lions and bears and everything else. They're going to go get in fights and do everything else. And why? The bottom line is they want to find a mate. Okay. So that's the number one thing. And then if you're a cigarette smoking male, that'll take another 2,250 days. So if you're out, you're single at the bar and you're smoking cigarettes, okay, and you have heart disease, then you're going to die pretty quick, right? So all of this stuff will take days off your life. Unmarried female, it's not a good thing either because you're doing the same thing, not as blatantly probably, but an unmarried female will in general take 1,600 days off your life. Okay. Overweight, a little overweight. If you have less education, that you probably won't live as long. You might not have as good a quality of life. So all of these things come into play. And then you get down here, a job with radiation exposure. And this is assuming you had 1 rem a year, which is quite a bit of radiation because most of the time you're going to get your reports back in millirem, not 1 rem, for 40 years. Okay. Well, an average take 40 days off your life. Okay. So the risk, even with as a radiation exposure, getting a fairly high level of radiation, it will take 40 days, a month off your life. And you accept that risk because you have to make a living. It's what you accepted to do to, live your life. Okay. So I thought that was pretty interesting. Okay. Now, what about pregnant employees? I talked about that if you're a minor in pretty much any industrialized country, I think now, that you cannot be in the room when x-rays are shot. You have to be out of the room, not even close. Okay. So anybody under 18, doesn't matter. You can't do it. Okay. But what if you're a pregnant employee? So what if, Sally, is your best tech and Sally gets pregnant. Okay. What do? And you own the clinic. Well, when you own the clinic, for the most part, in most small animal clinics, as far as the radiation guys go, it doesn't matter if you're DBM, what you're classified as a radiation safety officer or an RSO. You are the bottom line, buck stops here at your desk. If you own the clinic and you are the radiation, you're responsible for those employees to minimize their amount of radiation exposure. And the people that will regulate this will come in and get on you if you start getting out of line. Okay, so Sally comes to you as the radiation safety officer or owner of the clinic and says, I think I'm pregnant, and then what do you do? Okay, so the question to you is, can Sally continue to shoot x-rays? She's your best tech. She's your best tech shooting x-rays, gets the best quality films. If she's pregnant, yes or no? The answer to that is yes, she can. Okay, and you think, well, that's kind of weird. Okay, you can't let 18, anybody under 18, but you can let pregnant Sally in. Okay, and the reason being, there's rules on how this has to happen, and this is very important. Okay, the first thing that you need to realize is that the first trimester with pregnancy is the most susceptible to getting damaged by radiation. That's, again, your baby's just starting forming. You have a lot of cell turnover, a lot of making new things as this baby starts to grow, right? And so the first trimester is the most sensitive part. Okay, so what happens when Sally comes in and she thinks she's pregnant? Well, Sally comes in and it may be a month or two already into the pregnancy before she knows she's pregnant, right? So you're already halfway through the first trimester and she's already been shooting x-rays the whole time. Okay, nothing you can do about that. Okay, but here's what has to happen, and this is pretty much the rule in every state and probably Canada too, is that it's Sally's responsibility to declare she's pregnant, and she has to do it in writing. Okay, so Sally has to come in and tell the RSO or the owner of the clinic in writing in a letter that I am pregnant or I think I'm pregnant. Okay, once that happens, it triggers some events. Then the RSO or the owner of the clinic has to do a few things. One is they have to either move Sally out of the x-ray room and have her do other stuff that doesn't involve x-rays. Okay, or they have to declare Sally as a pregnant radiation safety worker. Okay, and then you have to do a couple of special things for Sally. And so you'd go to Sally and you'd say, okay, we have two choices here. One is you can go be a receptionist while you're pregnant and stay out of the x-ray room. Or if you still want to shoot x-rays and we agree on that, then we're going to do some special things for you. And what do you do as a special thing is you have to do what's called fetal monitoring. And so we talked about earlier, we saw the picture of the girl with the exposure badge up on her collar, right? And we said that for the most part, everybody wears those outside of the lead apron. Well, if Sally's pregnant and you elect to continue to shoot x-rays and be in the x-ray room, then you would order a second badge, and that's called a fetal monitor. Okay, you would continue to wear the one outside of the lead apron, which would measure the potential exposure, maximum exposure that Sally would get. Okay, the other badge is inside the lead apron. You wear it inside the lead apron at the level of the fetus. And that badge would measure the amount of radiation that somehow got through your lead apron that then could expose the fetus. And so you would wear both badges, two different badges, one outside the lead apron and one inside the lead apron for the term of the pregnancy. And that way you are doing what? You are CYAing, you're covering your ass, that you can prove that that fetus at Sally's belly level did not get any radiation. Okay, and that way, if Sally has a baby and unfortunately the baby comes out and something's wrong with it, you're covered. You covered your ass. Okay, otherwise they could blame it on you, and that's probably not a good thing. Okay, so the answer is can you have a minor in the x-ray room shooting x-rays? And the answer is no. Doesn't matter what. No. Okay, can you have a pregnant worker in there? Yes, you can, but you have to do fetal monitoring. You have to be careful. If you really want to make it sure that you're not going to, end up with a problem, then it's probably best just to say, Sally, why don't you go do something else? We'll, continue to hire you, and you can go do something else while you're pregnant, but let's stay out of the x-ray room during that time. Okay. But if they have to, what if it's your only tech, your small animal clinic, you only have you and Sally is running it? Then you may not have a choice. And so Sally then has to do fetal monitoring. Okay. Okay, minors and radiation, no, just no, can't do it. Okay, and then we have to learn about this other concept called ALARA, which is an acronym that you need to know, quiz-wise. Okay, and ALARA stands for as low as reasonably achievable. Okay, and this goes back to that linear model of radiation exposure, that the best you can minimize radiation, even though you're a radiation worker, if you can minimize the amount of radiation exposure, the better. Makes sense. So it doesn't say you can't get any radiation. It says to do what you want to do, you want to minimize the amount of radiation. So as low as reasonably achievable to be able to do a job as a veterinarian and get x-rays. Okay. Doesn't mean you can't do it. Doesn't mean you can't get any exposure, but as low as reasonably achievable. And so you'll see this ALARA concept a lot going forward if you look at anything about radiation exposure. Okay. So that is a really good time to stop for today. So let's stop the lecture today. We're going to pick up tomorrow and start talking about radiation physics.